Okay, good morning. I hope you are all fresh like myself. I actually lost my badge, but I hope you will still recognize me. So we basically are here today to hear a little bit about neuroscience. Don't be scared. It will be very understandable, I think. And I will introduce cortical.io. We are, if I get the slides to work. Yeah, now it works. We are a company from Vienna, Austria, and we work in the field of natural language understanding, which turns out to be a quite fundamental functionality that's needed in computer applications today. We're getting more and more text and information written by humans, supposed to be read by humans. And as you probably know, it's a quite hard thing to do to get computers understand what's in text, what's in emails, what's in documents. We are basically having a quite new approach in doing this after having learned that the state of the art, which is very much oriented on statistics, on hard number crunching, and that turns out to work to some degree, but it doesn't actually come even close to what a human of 10 years would be able to do. So we went to look for an alternative to this, and that's the reason why in our day-to-day work we basically do two things at the same time. We, on one hand, try to sort of work in a more theoretical way to find out a schema, a method, an approach to actually transform text data into something that can be understood by computers. And on the other hand, we take everything we've learned from that kind of research and we implement it as technology that we want to make usable in real world environments, in day-to-day use in business. So the fundamental problem that we try to address is in fact a simple question. How would you possibly represent something like the word cat in a way that you could compute using the word cat or the representation of the word cat in a similar way as we compute with numbers, which is very obvious. So in a first step to the semantic folding approach, which is actually our technology, we realized that it's not about algorithms, it's not about finding a way of sort of processing data, but it's actually fundamentally a method of representation of data. So the reason why we do this is because we face a number of challenges when we want to include textual data in our day-to-day processing. And much of the current state of the art, as I said, this is mostly based on statistics, on counting words and inferring the meaning from those word counts. But in the end, we face a certain number of problems when we do this. And I'm sure that you have encountered some of them. First of all, there is obviously the problem of quality. If you do a statistical analysis of whatsoever, it will never be as precise and exact as the real thing in the real world, precisely because it's a model that you create, and the model needs always to be simpler than reality. Another problem is the scalability. So we are now in the age of cloud computing and so far. So in principle, we think we have endless computer resources, but it turns out that if we try to do word counting statistics on sufficiently complex text, the system could basically compute forever. So very often we are in a situation where even if you have endless computing resources, you will not be able to actually go to the depth of things. So scalability of those systems is key to bring it to function practically. Then, of course, there is a more complicated approach in the sense of efficiency. So if I want to teach my computer how to understand certain things, I have to train first. So in the age of machine learning, training of computer algorithms became the day-to-day job. The problem with text is very often that the system can only infer very superficial semantics, or the meaning of the text. And because there is such a tiny amount of semantics with every email, with every text that we ingest, we need a lot of that material. And interestingly, I mean, people typically say we are swamped in data, we don't know what we could do, there is more data than we can actually process. But as soon as you try to sort of straighten out a specific problem practically, you realize that for your very problem, there isn't enough data. And I could give you an example that we've encountered in the context of banking, for example. So the goal was basically to ingest emails and to detect if some inside trading or some regulator-driven restriction was basically identified in emails. And there were a number of companies, startup companies like we are, who were trying to sort of cope with that challenge. And in the end, many of those machine learning approaches said, yeah, we could have done better, but unfortunately, we need more material in the context of this fraud detection. So if you could provide us with some 20,000 fraudulent emails, then we could, of course, train our system very well. There you see, that's one of these problems where you will never find a solution with that approach, because there simply is not enough data to do this. Then another problem that is very crucial, especially in regulated environments, is you might be allowed to, for example, find out that a certain customer could get another interest rate than another customer, but what you need, or what the regulator actually wants you to do, is to be able and explain why you have made that decision. And with a lot of those modern machine learning approaches, it's simply just not possible to analyze and give a concrete reason why a certain example or a certain result has been chosen. So it's very important whenever you have computer systems infer some reactions, some decisions based on data, that you're also able to explain why certain decisions are made. So it's also very important that any algorithm that you apply practically is understandable, is readable in a logic sense for humans. And then, of course, there are problems like the repeatability. You might have seen, if you have been working in the domain a little, or if you have been trying to get solutions based on machine learning, that every single sort of feature that you want to create, let's say you want to basically ingest emails, let's say, and you want to filter out every email where a customer complains about something, you can do so. You train what's called a classifier that classifies those emails into complaint, non-complaints. If the next day you would want to get emails out where people ask a specific question, let's say about a product, you have to start the training all over again. So every problem needs its own training procedure and its own training data to actually get to a result. So basically the repeatability is not easy to achieve. Best thing would be like with a human, you teach the human how the business works, and then the human could actually adapt to all the variants of questions that you encounter. And this is something very hard to do with machine learning. Okay, so basically if we look at all those constraints, we realize that in the end working with text in a more systematic manner is typically very expensive, it takes a long time, and when you start a project basically to solve a certain business case, you can never be sure that you actually find a solution to all of this. Okay, we tried to find an alternative, and the alternative, of course, has to be fundamentally different because as soon as we start, in fact, to have a statistical approach, we will basically fall into this problem zone again. So we have to choose something very different, and the way how we do this is, if you want a very naive approach, because the only reference implementation of a system that understands language is the human brain. And for that, we were actually looking into neuroscience to get, if you want, inspiration or ideas on how we would possibly find a different solution. So what we did is that we took very recent brain research, specifically one from a researcher called Jeff Hawkins in California, whose work basically focuses on the question, how is the neocortex, so that's the part of the brain that actually does the information processing where our thinking basically happens, how does the neocortex work with information in a general fashion? And he came up actually with a pretty sound explanation of mechanisms in the neocortex that explain how that data in general is processed. And what we said is, if data in general is processed in that way, language data will be processed in a very similar way. So we took the theory, if you want, on brain computing from the actual brain, and we tried to take this as constraints to find a solution in implementing this using computers. So we do have a lot of support from actual neuroscience. So there is recent research that shows basically that this is an fMRI. So this is a picture made from a living brain of a person that, in that case, actually has the task to think of or imagine words like celery, airplane, and so on. And what happens is that the fMRI takes a picture of the activity of the brain. So what we see here is basically the brain seen from the top, and the more red you see in a certain region, the more active that region is. And the interesting thing is that the pattern, by looking at the whole brain, in fact, the pattern for a given word or a given image stays very stable. It stays stable to a degree that whenever the same person hears the same word, there is a same pattern basically appearing in the activity of the neocortex, which means that there is some form of, I would even say, organic representation of information within the brain. So what Tom Mitchell, for example, here from Carnegie Mellon, what he did is he tried to make pictures of a number of words, and he trained a machine learning algorithm to basically find the way back. So for a given picture, the system was then able, after having been trained on a specific person, to actually give back the word where the system thinks was the originator for a certain image. And that actually worked pretty well. What became a little scary even is that this did not only work for the pictures of a specific person to be computed back into its sort of semantic content, but this also works across people. So the system could be trained on one person's sort of recognizing of words, and with that trained system you could even read out the representations of other people, which of course makes a lot of sense. If there wouldn't be any similarity between our internal representations, we would not be able to have a conversation because we would sort of live in different conceptual words. So that research has even been extended further by a group at the MIT. So this looks a bit funny because these are brains that are unfolded and flattened out to actually give some sort of map of the patterns that you see. And again, the color coding represents the activation of different parts of the neocortex. And what that group was able to do was actually to map across people 900 different terms that could be differentiated by the algorithm in a fully automated way, which basically leads us to the concept that every word in the brain basically has an activation pattern. And that was the starting point for our approach. And we tried to come up with a model that actually is capable of doing such a, let's say, two-dimensional mapping of semantic content. And the way we did this is by sort of mimicking what humans are actually doing. So to start with, you have to train a system in the very similar way how we have to train our brains. We learn to speak and we go to school, learn to write and so on. And because we don't have 30 years of training time available, of course, we have to come up with a much quicker way. So what we do is we take reference information. And in this context, reference information is to be taken literally. So it's school books, if you want, mostly, of course, textbooks from university about a topic, and we we extract the text from those textbooks, and by applying a specific algorithmic approach, we distribute the information that we extract from those textbooks onto a two-dimensional map. So here, for example, let's say we want to train a system on general English, and let's take, for the sake of an example, let's take Wikipedia. We extract all the 5 million and something pages of Wikipedia. We cut it into little snippets of text so that every snippet basically speaks about a specific topic as possible. And then we distribute those snippets over a two-dimensional space in a way that snippets containing similar terms stay close together and snippets containing different terms stay proportionally far apart as their similarity is given. So that's the first step. It works fully automated, so you have only to present the data and the system does the processing accordingly. So after that step, we find every snippet that we extracted from our reference information at some given point on our semantic map. In the second step, what we do is we extract all the words. That's basically the dictionary that the system has generated, all the words that were part of that training corpus. And for each of the words, we ask the question, in what snippets do you appear? And as those snippets have been distributed across this grid, which happens to be 128 times 128, it could be any other size. The size just turned out to be practical for technical reasons. We activate all the locations where a snippet actually contains the word out of my dictionary. So just to give you an impression, in Wikipedia, for example, you end up with some 800,000 around distinct words. And for each of the words that appears there, what we get is a pattern, as you see here, for the word Socrates, classical, and so on. After that, all the training is actually finished. And from that moment, we only keep working with what we call the semantic fingerprints of each of the words. Interestingly, that whole procedure is completely independent from the actual language that we use in the first place. So this works for all different languages, even languages that are pretty different in structure, like Chinese or Arabic, from the European ones. And what you can see here is that obviously the representation as a fingerprint is independent from the actual string, from the actual word that has been used. It is proportional to the meaning. And as a consequence, as you see here, the word philosophy, basically converted through systems trained on different languages, always ends up with the same fingerprint, which is very handy because what we can now do is to basically convert any language into a fingerprint that stands for the content of the text that we have used. Here you see a little bit of the anatomy of such a fingerprint. So for example, the word organ, English word organ, very obviously an ambiguous word, so it has different meanings, it has different contexts. And what we can do is we can inspect by looking at the locations where the fingerprint has activation patterns. We can, as if you remember, there are snippets from Wikipedia, for example, located at those positions. We can look at them and we can extract the words that we find there. So you have a region here, for example, like the context 2A, containing words like composer, baroque, music, score, all things that to some degree are in relation with the concept of organ. At another location, you find words like piano, guitar, trombone. So again, contexts of the word organ in a slightly different approach, only musical instruments. Then in a third context, you see words like liver, heart, and muscle. Very obviously another sense of the word organ that has its activation patterns at a different location because we have this semantic map that sort of distributes those patterns. So what you see here is basically the solution to a very fundamental problem in natural language understanding on how do you represent words that have different meanings. Here we see that by sort of scattering those activations over a two-dimensional structure, we can see all these meanings simultaneously without that they actually interfere. So these are word fingerprints, which is nice, but it's of course not enough to actually get a really deeper understanding of a piece of text. So the next stage will actually be to aggregate those words to generate fingerprints of things like sentences or paragraphs, books, or even larger structures. And the very simple approach that we can apply here is that for a sentence like organs and pianos are musical instruments, the only thing we need to do is to convert every individual word into its fingerprint and then to aggregate those fingerprints, which means adding them together. In the end, we get a fingerprint that actually stands for the whole sentence. And the nice thing here is that there is no training involved anymore because we have the atoms of the semantic content defined by fingerprinting the words, and from there we can, by just adding and subtracting those representations, generate fingerprints of basically any size information. You could, in fact, instead of taking a sentence, you could take the content of all books of a library, and you would end up with a fingerprint for the library, basically giving you an insight on what are the topics, what is covered in this library, what kind of library is this, and you would have a fingerprint to actually represent it. So the reason why we do all that is, of course, that we want to apply some sort of operator on this representation. And the only operator needed is what we call the basic similarity of the two fingerprints that we generated. And the way how we measure the similarity between the two is by literally putting one on top of the other and counting how many common bit positions do I have between two fingerprints. And the more of these common positions are activated, the more similar the two words or texts or paragraphs or whatever has been fingerprinted are. So you see here in the upper line, for example, two sort of words or phrases, done deal and signed contract. So anyone in the business world immediately realizes those two sentences basically represent something very similar. And if we look at the fingerprints, we find out that about 30%, which is quite a lot, of the 300 or so pixels that you see of the bits actually keep the same position. So they overlap by 30%, which means the two phrases are pretty similar. If we change, and you see this in the lower line, one side to something more unrelated, you see Star Trek, for example, only overlaps by about 5%. And believe it or not, that's enough to actually go into a whole new other category of understanding text, because we keep converting pieces of text out of emails, of documents, into those fingerprints, and we can, by comparing it to stuff that we know, basically measure how close the meaning of what we know is with a piece of text that is to be investigated. And what is also noteworthy here is the fact that there is not only a quantitative measurement, so how many overlapping bits do I have, but there is also, by looking where the overlap happens in the fingerprint, I can also give a qualitative measure. So I can say done deal is very similar to signed contract, very similar because I have 30% overlap, but I can look at a specific location where some overlap happens, and I can see words like investor, liquidity, shareholder, and so on, which is the context for the similarity at a given position. To be precise, that system, for example, has been trained on what we call investment bankerish. So we have taken books, literature from investment banking to actually train the system and to be able to understand that specific kind of jargon. So what can we do now with a system that is capable of converting any piece of text into a fingerprint and that is able to compare the similarity between two fingerprints? One thing is we can compute the ambiguity of the term. So what we do is, again, with my example from before, we start with the word organ, and we ask the system, what is the word that has the best matching fingerprint within the list of all the words it knows? And the system comes up with the word liver, very obviously, because that liver cluster on the right, if you remember, is sort of the biggest. This is due to the fact that Wikipedia just happens to contain more information about biology than it does about music or performing arts. But the first term, so to say, that has the biggest overlap is the term liver. What we can do now is we say, if we take away all the liver dots from the organ representation, and we ask again what is now the most similar, we get the next biggest, so to say, word that comes into it, which is the word piano. We can continue this, and in the end, we disambiguate the term organ into all of its component meanings for which we get a fingerprint, practically speaking. Another thing is that we can generate terms that match in the context with the central term, like for the term Socrates, we can ask for associative nouns and we get mind, truth, wisdom, and so on. So we can characterize words by finding other words that relate to it. We can do search. So if I have a collection of documents, I can convert these documents into fingerprints and I can ask the user to enter whatever query he has or point me to an example document. I can ask which are the documents that have the biggest overlap with my given query, and I can sort of rank them or give the result in a decreasing rank of overlap. That, by the way, if you remember, works across languages. So I could, for example, index a collection of English documents and I could formulate a German query and the system would still be able to match the content of both. We can classify documents. Here, for example, I have animal names and I want to split them into mammals and non-mammals. I can literally take the word mammal as a classifier. I generate a fingerprint and I match it to the animal names. And when the overlap is big enough, the animal is in fact a mammal. And if not, there is no to very little overlap. I can extract keywords. I just go through that. These are all basic functions. And I can cut a large text into little context snippets, again, by generating fingerprints and looking where the topic changes from one topic to the next. So as a result, we end up with a new approach in representing and computing with natural language, which is very simple. There is one algorithm, one operator, one data format. So it's very simple to imagine how this works, which makes it, again, much simpler to figure out the solution strategy for solving certain problems. It works very efficiently as it is a binary representation. You can do a lot of computation in very little time. So we can process literally terabytes of text data on a notebook if needed because the computation is so inexpensive. The whole thing is currently packaged into 3 core products. One is the actual semantic engine that does the conversion of any given text into a fingerprint. We have a search system that actually generates an index of, can even be large collections of hundreds of millions of documents, where we generate fingerprints for each of the documents and can search through them. And it's a semantic search, so you can find documents that do not even contain a word from the query, because the matching happens on the meaning and not on the literally string representation. And the third module is basically used to look inside of documents and to extract key information from things like contracts, for example. So we have a number of projects currently where we work with things like credit agreement collections or lease agreement collections, and we extract information from there. In fact, as you can imagine, by understanding text, you can do a lot of things. Whenever text appears, you can figure out what it means and you can decide what you do with it. You can find documents, you can match people. Let's just imagine if I take LinkedIn profiles of people, I create a fingerprint of a LinkedIn profile, I can literally match 2 profiles by overlapping 2 people's LinkedIn fingerprints, if you want. And that actually works literally. So that's one of the aspects of the approach. You can have a very naive way of trying to solve certain things, and it's astonishing how well it actually works out in the end. These are basically use cases that we have practically implemented, and probably the first thing you see is that they're coming from all sorts of industries. We do have, of course, a lot of activity in the financial sector, where, as I said, we can index large collections of documents. We work with things like credit agreements and extract key information from there. We can monitor email, for example, when it's about compliance monitoring and similar things. So we basically keep applying the method of taking the involved text, converting it into a fingerprint, and comparing it to some reference text. The reference text, just as an example, could be the formulation from a regulator about something, and you could match your own product descriptions with what the regulator has asked you to sort of implement at the level of product descriptions, and you can literally match how well is my marketing text for a new product, for example, compliant with the regulator requirements. We do have a more detailed view, which I cannot show here, would take another hour, but I invite you, of course, to join us at our table if you have further questions, and I can give you more precise explanations on how all these use cases have been implemented. We do this now routinely in the sense that we start with a proof of concept on your very specific use case, which in a couple of weeks can be sort of measured to what degree the approach actually can help to solve your problems here. So I stop here, and I invite you, if you have questions on the topic, I would be happy to answer them. Thank you.
Do we have any questions for Francisco?
CRM vendors or omnichannels or tools like Nuance, for example, or Dynamics, or how you is it best of breed, the thing that we added, or do you have some
we do have partnership, but not so much, at least at the moment, on the technical side, but much more on the business side. So we work with PricewaterhouseCoopers here in Europe, for example, especially in the financial domain, because they bring in the subject matter expertise that is needed. So in our approach, what is key, of course, is to, for example, select the right training material in the first place. So the system only works as good as you can capture the semantics of a specific domain. And let's say for legal reasons, for legal topics, you need to have the knowledge on what kind of training material is actually referenced here. And that's the way how we work with our partners, is that they bring in the expertise in the topic domain. They help us select the right training material to create the gold standards that we need to measure the quality of the output and things like that. And so by joining up forces, we can solve also quite complicated problems in specific domains. So we plan to have this in several, so also in life science, to find experts in life science and so on, to adapt to all these business areas.
So, Francisco, that was a very good presentation. And actually, one of the questions that I have is about the performance of your algorithms against pretty non-standard languages. So for English, for German, French, Spanish, perhaps Portuguese, it would work good. However, if you take into account more exotic languages, we observe that many times when implementing chatbots and so on, so for Polish, for Arabic and these kind of things, it's a really serious problem and actually prevents to start fast. So what is your view? Is there any remedy, or it just takes time to...
No, in fact, the system is agnostic to the language. So if there would be enough material available, you could train the system in Klingon, for example. It should work as long as the reference literature in Klingon has the sufficient quality. So in fact, the system is completely agnostic to the language. As long as we have symbols, as long as we have a grammar, as long as we have maybe some morphological aspects, the approach can be applied straightforward. Interestingly, because we don't need to train on the actual payload data when we face a certain problem. So normally, for example, if you want to machine learn or teach a system to understand medical records, you give it 5 million medical records, and then it knows how to judge on the content. But of course, a human would never become doctor by just reading, reading 5 million medical records. What you would actually need to do is to read textbooks, to read generic reference information. So the nice thing is that there is basically no professional environment in any language where there is no reference literature. Why? Because people in that domain have to be have to become experts. So the nice thing of the approach is that even while not knowing all the possible application areas, I'm quite confident if there is some human expertise needed in a certain domain, in a certain language, there will be enough data for us to train the system. And we can mechanically, if you want, align semantic spaces in different languages in an automated fashion that not only allows us to understand Chinese text in the same way as we would understand English text, but we can even cross those barriers. So we can take the very same content in English or in Chinese, and we can immediately compare it on the meaning.
Hi, my question would be, do you have a specific use case for banking and financial services? If you could explain about it.
Yeah, we do in fact have a number of them. I can maybe go forward here. For example, you have email compliance monitoring. So it's about monitoring streams of email. In that case, it was so the conversation between a broker and his client. And at some point, the broker used some metaphorical language saying, last week I became member of a frequent flyer program and I made $5,000. Yeah, so if you just look at the words, you might not find out that they were talking about some sort of non-public information. But by looking at the fingerprints, what we could realize is that there was a certain email where suddenly a certain topic appeared, namely frequent flyer program, which was completely unrelated to anything in the context. And by applying a number of those filters on the semantic side, you can identify unusual emails, which you then forward to the compliance officer who can judge on the relevance. So this is not a direct solution, but a filter like that can replace thousands of regular expression kind of filters that are currently used. And what is important, it creates practically no false positives. Yeah? So there is always a real reason for an email to come up. There are others. We have done the risk analysis of credit lines, for example, by looking at credit contracts and comparing clauses in these credit contracts. There is the analysis of customer intent, for example, to find out if a customer calls in the call center for some reason. You could, by looking at the fingerprint and analyzing it, for example, find out that that very same customer could be a good target for an insurance product and things like that. And then, of course, one of the most widely applied uses of our technology is in the field of contract intelligence. Whenever, for example, like a recent regulator requirement from the IFRS 16 regulation that now says that you have to bring lease agreements into your balance sheet. And what we did is that we could analyze thousands of lease agreements and basically extract key information to ensure if they can be actually put on the balance sheet right away. And we, by doing so, we could replace service providers basically offering hundreds of attorneys work in doing that manually. And the interesting thing is that we found this only after sort of creating our solution there. Interestingly, human annotators, so attorneys, for example, achieve only about 60% agreement on how to work on this document. So not only was the machine like several thousand times faster, but it ended up also to be much more precise and constant in the quality of the output compared to human work. So here, for example, we also worked with ISTA documents where we extracted a number of typical items from the documents in a fully automated fashion.
Great. Yeah. Unfortunately, that is all we've got time for this morning. I know there are a couple of you with additional questions. Francisco, you're sat at table...
Cortical.
6? Six. Thank you, Sylvia. Yeah. So if anybody does have any further questions for Francisco, then do feel free to check him out on table 6. I'm sure he's more than happy to answer any further questions. Folks, big hand for Francisco for kicking things off.
Thank you.